Okay, good afternoon. Let's get started with today's lecture. Today we are going to continue addressing this topic on warehouse space and layout planning. This is going to be part 2 of this lecture, which was started last week on Wednesday. And the idea on Wednesday, we look at the planning of a warehouse from 2 different philosophies. So we look at the difference between randomized storage philosophy and also the dedicated storage philosophy. And we address the differences and also look at ways in terms of planning for the capacity. And if you are looking at dedicated storage space, we were able to compute how much space will be needed. If you're looking for a randomized type of storage, we were also looking at computing how much space was needed. So today we're going to continue our discussion. Today we are going to use a different strategy to assign product to locations in a warehouse. Specifically, we are going to be using operation research, optimization models, like linear programming models, in which we're going to define an objective function, some decision variables, and some constraints. And then we're going to present a way to solve this problem without having to use the simplex method or to rely on a computer. I'm going to present an example or a method, more like an algorithm, that is used to solve this optimization problem. And from there, we're going to transition to talk a little bit more about the different type of equipment that is you can use in a warehouse, and that will be the last piece of this lecture. So before I get started, is there any questions? Okay, so as always, I start the lecture with the objectives for this course, and we are with the material that we are covering today. We are addressing objective number 1, which is to develop an understanding of the principles of facilities location, layout, and material handling systems, and to practice designing facilities. In this particular lecture, we're focusing on the design of warehouse facilities. So the agenda for today, as I mentioned already, I'm going to present a brief introduction, more or less a review of what we discussed last time. And then we're going to go into the warehouse layout model, which is an optimization model. We're going to present the optimization model and then a way of solving this problem. And from there, we're going to do an example. And then at the end of the lecture, we're going to focus on storage systems. So I'm going to be presenting some pictures and talking about some of these different storage systems for the warehouses. So the learning objectives for this lecture is to learn warehouse operation improvement through the application of best practice procedures and available material handling systems for warehousing operation. So as we discussed in our previous lecture, there are different types of storage. We talk about the randomized or floating storage, which is used when a product unit or stock keeping unit can be stored in any available storage location. And then we also discuss the dedicated storage, which is used for a unit of product or when a unit of product is assigned to a specific location in the warehouse facility. So we saw that for dedicated storage, we needed more space because we are going to reserve a space in the warehouse for that type of product. And if we have another type of product, that cannot be placed in that location. For randomized, we don't have that constraint. We are not reserving any piece of the warehouse to any product. So any product can be stored in any available storage location. And then we saw that there are strategies that combine both of these philosophies, which are variations of dedicated storage. This storage according to a part number sequence, storage according to the level of activity, and inventory level. So those are the type of storage. From a pictorial representation, we have dedicated storage here at the top, and then random storage. You see dedicated storage have those colors grouped in an area of the warehouse. So for example, you have those light green colors. That means that you have that space occupied by a specific type of product. Same thing here, the dark colors and the green color. So, and you can observe the difference between that and the random storage philosophy, in which you don't have a group of squares that are grouped together with the same color. Again, these policies are also affected by the location of the input and output docks. For example, if you have this product that is in green, that is a product that moves frequently, you will try to locate those or that product family in a location that is close to the input docks. Same thing if you have a product that is moved frequently or has to be shipped frequently, you'll see that those will be located close to the output docks. But the idea of this picture or these figures is to show the difference, right? So you can easily, at the top, you can easily identify where the products are, whereas at the bottom, those products can be located anywhere, which will add more challenges when you're trying to put together an order. But at the same time, for the random storage, you might not need as much space as were for dedicated storage. So what are the objectives of warehouse layout planning? Again, we want to make sure that we use the space, effectiveness in space usage, material handling efficiency. We want to minimize the cost of operating the warehouse. We want to have some flexibility and also being able to keep the house in order. So for those purposes, we can now define what is known as the quantitative warehouse layout planning model. So if you're familiar with operation research, optimization, this will be a review. If you're not familiar with operation research, you're from manufacturing, it's not going to be a big challenge. I will go through the steps of formulating this problem. And again, we are not going to solve this using any specific operation research strategy. We're going to define an algorithm to solve this problem, and that'll be easy. So let's look at the warehouse layout model. So this model is trying to define the location for products based on the dedicated storage philosophy. So we have a set of storage locations assigned to a specific product. And then we're going to have a decision variable that is going to be a binary decision variable, meaning that we have a value of 0 or 1. And it's going to be equal to 1 if a product J, which is one of the product families, is assigned to a location K. Okay, if that's the solution, or after solving the problem, we get a 1 for specific location and specific product, that means that that product is going to be assigned to that location. If we get 0, then that means that the product is assigned somewhere else. So for example, X11 means that product 1 is assigned to location 1. And if that's equal to 1, then we know that product 1 is going to be assigned to location 1. If it is equal to 0, that means that that product 1 is assigned to another location. So what is the measure of effectiveness for this model is going to be to minimize the total expected distance travel. So we want to find the best location for all our product families inside the warehouse. So we are minimizing the amount or the total expected distance travel from moving the product inside the warehouse and outside the warehouse. So what would be the input data? we're gonna have information about the number of storage locations, and that parameter, we're gonna name that parameter Q. N is gonna be the number of products. M is the number of input-output points, meaning the doors for the warehouse. Sj is the number of storage locations required by product J. Okay, so let's say product 1 requires 10 locations in the facility. So Sj, S1 is going to be equal to 10. Tj is the number of trips in, out of the storage for product J. So how often are you moving this product? That's going to be Tj. Again, J is identifying a specific product. Pi is the percentage of travel in and out of storage from point to from point I. So how often, I mean, out of the number of times that you are moving this product, how often is this product being moved from door 1 or door I, or is using door I equals 1 or I equals 2. So if, let's say we have 2 doors, this product is being moved by door 1. How often is moved through door number 2? So that will be the percentage of travel in and out of storage 2 from point I. Dik is the distance or time required to travel from point I to location K. Okay, so how far are you located from the door to the location that is assigned to this product? And as a note, we will use rectilinear distance between storage centers. Okay, so that's what we're going to be using to measure these distances. So the mathematical model, actually, let me define. The mathematical model, again, let me summarize. So we're gonna define the mathematical model using these parameters. So we're gonna have, again, the decision variable. Or multiple decision variables. So the decision variable is going to be named in terms of J and K. Those are the indexes. And this is going to be equal to 1 if product J is assigned to location K. So in this model, J is the set of products and K is the set of locations. So capital J is representing a set of products. If you have 10 products, that's going to be 1, 2, 3, 4, 5, up to 10. So little j will be representing an element of this set. Same thing for the locations. Capital K is the number of locations. So if you have 100 locations in your warehouse, then that will be part of this set. So location K equals 1, K equals 2, K equals up to 100. So xkj equals 1 if product j is assigned to location K. The objective function so this is what we're going to use to make decisions. Our decisions are going to be based on these objectives. Right. So, for example, if you are making decisions in order to minimize costs, You're making decisions in order to maximize profit. You're making decisions to minimize the number of workers. Those are the objective functions. In this case, our objective function is going to minimize the total distance traveled. So this is going to be minimization, minimize z, which is the summation from j equals 1 to n, which is the number of products of this ratio Tj Sj times the summation for the locations k equals 1 up to q of this expression, summation of I equals 1 up to m of those frequencies pi times those distances from I to k. And all that multiplied by the decision variable. Okay, so I is another set. So let me write that somewhere. I is another set. This is the set of input, output points, or the doors. And we're going to be measuring the distance from each door to the location of the product in the warehouse. So this expression is minimizing the total distance traveled. So we have the decision variables and the objective function. Now we want to define our constraints. Okay, so we know we want to make decisions in terms of where to place each product in the warehouse. We know we want to make those decisions based on the distance travel, and we want to minimize distance travel. So our decisions are going to be directed towards that objective function. And now we have some constraints. They're basically constraining our decisions. So these are the constraints. First constraint is the summation for j equals 1 up to n of x jk has to be equal to 1. So j's are the set of products, and this constraint will be from k equals 1 up to q. So what this is saying is only one product can be assigned to a specific location of the warehouse. Okay, so we are making the summation of every product in the facility that's going to be located in the facility, which is going to be assigned to a location. For this case, it's going to be location 1. We want to make sure that we only assign a single product to each location. So this is saying is only one product type J can be assigned stored in each storage location. Okay, so that's the first constraint, and we're gonna have another constraint that is a complement to this constraint. So basically, in the first one, we're saying we can only assign the product family to each location. And now we want to make sure that we assign all the locations that are needed for each product family. Okay, so that's the other constraint. Summation k equals 1 q x jk equals the number of locations that are needed per product. This is for j equals 1 up to n. And again, what this is saying is the following. We assign the required number of storage locations to each product J. And that's the model. Okay, we have a decision. We're trying to assign each product to a location in the warehouse. We have two constraints, and we are making those decisions based on the total distance travel. We want to minimize the total distance travel from the location of the doors to the location of the product in the warehouse. And we want to make sure that we only assign one product to a location. And we also need to make sure that if we need 10 spaces for product 1, we are assigning those 10 spaces for product 1. If we need 20 spaces for product number 2, that we assign those 20 spaces to product number 2, which is SJ, which is the number of storage locations required by product J. Okay, so this is the same mathematical model, just in a clean version of the mathematical model, the same thing that we defined here, but just the equations. So we have the objective function. Again, xjk is our decision variable. So we are making the decisions based on the total distance traveled. We want to minimize that. And then we have two constraints. One that is making sure that we assign only one product to a location. And then the second constraint is making sure that we assign the total number of spaces needed per product to each product. So if you are familiar with operation research, linear programming, you know this is a linear programming model. All equations are linear. So you can solve this problem using the simplex method, or you can use a computer to solve this in Excel. Again, Excel will implement the simplex method for you, or AMPL, or any commercially available software. But for the purpose of this class, because I know some of you are not from industrial engineering, we're going to define an algorithm that will help us solve this problem without having to solve this using the simplex. So again, this is the objective function, and we can define a function based on these two parameters. We're going to call this fk. Fk is going to be equal to the summation from I equals 1 to m for the frequency of movement of that product I times the distance traveled from door to the location. So this is going to be the expected distance travel between storage location K and input output doors. Then if we substitute that FK into here, that's what we are doing. Now this portion right here is just the multiplication of FK times XJK, which was already here. Note that this expression, if you expand that expression, it will look like something like this, in which you're going to have a ratio Tj over Sk multiplied by this expression of, or linear equation of F1 times Xj1 plus F2 times Xj2 and so on until you cover all possible combinations. And we're going to use that to solve this problem. So the solution procedure, basically, we're going to use this result to establish our algorithm, which is summarized in this slide. Our first step is to relabel the products 1, 2, up to n according to the non-increasing order of their Tj, Sj values. That's based on these ratios. And we're going to find the values of Fk, which is the expected distance traveled between location K and the docks or the input-output doors. We're going to find the of Fks, and then C, we're going to assign the locations to products according to their F values from lowest to highest. Okay, so step 1, we're going to relabel the products 1, 2, up to n according to their non-increasing order of their Tj over Sj values. So we're going to find all possible ratios for all products. Then we're going to find the values of Fk, which is the expected distance traveled between location K and docks. And then we're going to assign the locations to products according to their F values from lowest to highest. So let's look at one example. Okay, we have a warehouse, has dimensions 40 feet times 40 feet. And we have storage locations that are of size 10 feet by 10 feet. We're going to have only one receiving dock at the northeast corner of the layout and one shipping dock at the midpoint of the west side. We have two products, A and B. Product A requires 100 pallets per week. Product B, 80 pallets per week. For product A, we require 10 storage bays. So SA is going to be 10, and product B requires 4 storage bays. SB equals 4. So we have again a warehouse with the following characteristics: 40 by 40. That means if we have 40 feet here, even though it's not up to scale, right? But this is 40, and this is 40. And each of these boxes is 10 feet wide. And also 10 feet in this direction. Okay, so we have those dimensions, and those dots in the figure are representing the location of the doors. So if you're going to move something out of this warehouse, you have to use this door or the door at the top right corner. So what we are gonna do now, we're gonna compute the distances for each or the F values for each one of these locations. K. Okay, so we are going to assume that P1 is 50% and P2 is also 50%, which means that there's the same chance of you using either door. So you have a 50% of using one of the doors, or you have another 50% of using the other door. So there's no difference. Same probability of using either door. So we are going to compute Fk, which is going to be equal to the summation I equals 1 up to m of pi dik. And this is for all possible locations. So this is for k equals 1 up to, in this case, we have 16. Right? We go from 1 to 16. So if we expand this for this particular problem, Fk is going to be equal to P1 times D1k plus P2 times D2k. So if we look at location 1, this is going to be location 1. We are going to find F1 for location 1. We know there's a 0.5 probability. And now we have to find the distance from 1 to 1. So I'm going to name this one 1 and 2. So this is going to be k equals 1 and this is k equals 2. The opposite. Let me rename this quickly. This would be k equals 1. And this one, it doesn't matter. Okay, you can name one or the other, 1 or 2. The idea is that you use the corresponding distances. Okay, so what would be the distance from 1 to 1? We're going to start measuring that from here, from the centroid, this centroid, this centroid, this centroid. So this is 10, 20, 30, and then 35 and 40. So that D11 equals 40. And now we're going to measure the distance. Probability of going through door number 2 is also 0.5. Okay, so those values were given. And now we're going to find distance 2, 1. So distance 2, 1, go from here to here, from here to here, and from here to here. So that's 20. So this is gonna be equal to 30. And I have to repeat this process for every square. Okay, I need to find the value of F for each square in this warehouse. So if I do, say, F2, use a different color. So this is 2. It'll be 0.5 times the distance from 2 to 1, right? So we go from here to here. That's 10, 20, 30 plus 0.5 times 10, 20, 30. So that's also 30. And we can continue this process. I have F9. So F9 will be this one. So you'll go from here, use another color. So for F9, three 0.5 up to 1. Here, here. So 10, 20, 30, 35, 45, 55, 50. So 50 or 60. 10, 20, 30, 35, 40, 45, 50, 55, or 60. Plus, here is 5, so it's 10. 0.5 times 10. So we 35. Yes. Yes, the 60. So good question. So I'm measuring the distance from each centroid for each square. So I'm looking at F9 now. So I'm going from F9, which is this square, from this centroid to this door. So this is 10, 20, 30, 35, 45, 55, 60. And those are rectilinear distances. So I got the 60 from going from the centroid to that door. And now the 10 is from this centroid to this door. So it's 5 and 10. And then we multiply 60 by 50%, and then we add 50% of 10, that's 35. And if we continue this process, can give you a couple more. But again, for you to solve this problem, you're gonna have to look for each F value for each square. So we'll have 16 at the end. So F15 is gonna be 0.5 times 50 plus 0.5 times 40. And this is going to be 45. And then F16 going to be 0.5 times 40 plus 0.5 times 50. And this is also 45. And those are given, you can verify those. But again, you have to go and create the list from F1 to F16. You understand the process now. Okay, so you look for the distance, you multiply by the probability of using that door plus the other distance by the probability of using that door. What if you have 3 doors? Well, the expression will go, these probabilities will have to add through to 3, right? So you're going to have a probability for that third door. And this expression, instead of having 2 terms, will have 3 terms. If you have 4 doors, we'll have four terms, so on. So from here, once you compute all F values, we get to this point in which we define we are going to enter the values of F that we just computed. So this is 30, this is 30, 30, 30, 30, 30. So these are all 30s. This is 35, 35, 35. So those are F values, 45. Okay, so this is F11. This is F. Sorry, this is F1, F2, F3, F4, and so on. So once we have all these F values, we assign those values to each cell in the warehouse. And now we have, remember, we have 2 products. So the idea now is where in this grid you assign product A and product B. Okay, so for us now, we have to identify a way to prioritize these 2 products. If you remember from the algorithm, we are going to relabel the products according to the non-increasing order of TJ over SJ. Okay, so we're going to compute this ratio for each one of the products. In our case, we have 2 products. And then we are going to assign a priority based on that ratio. So the product with the highest ratio will be placed first into the warehouse based on those F values from lowest to highest. So if we look at the ratios, TA equals 100, SA equals 10. So that ratio TA by SA is 10. TV equals 80, SB equals 4, TV by SB equals 20. So TV over SB is higher. So we consider, since TV over SB is higher or equal to TA over SA, consider product B first and product A second. So we are going to assign B first, and then we are going to assign product A. So what these ratios are telling you is that you have, let's go back to the definition of these ratios. TJ is the number of trips in and out of the storage, and FJ is the number of storage locations required by the product. So obviously, if you have a product that is moving more often than other products, you want to place those products in a location where you have a shortest distance to be traveled. Okay, so that's why we look at these ratios. We want to make sure that we rank them in terms of this ratio of space, of traveling frequency by space, and then those that are ending up having the highest ratio, meaning that they're moving more frequently, we want to place them in the locations that have the shortest distances in the warehouse. So that's what we are trying to do here. Once we have all this, these are like weighted distances, and we know that B moves more frequently than A, we want to put B in those locations where the distances are smaller. And we want to place those first, right? So based on my solution, and based also on the information that is given by the problem, this is telling me that B requires 4 spaces. And this is telling me that I'm going to assign B first based on this ratio. So I'm going to place B, I'm going to reserve 4 locations in this grid for B, and I'm going to make sure that I use those that have the shortest distance. So in this case, I have more than enough. I have 8 with the same amount of short distance, which is 30. So I can use 4 of those to assign B, and then I can use the rest to assign A. So what I'm going to do, again, you can choose any of the locations that have a distance of 30, which is the minimum. So I'm going to assign this, and this for B. So B is here, B, and D. And then A requires only 10. So I'm going to assign 10 to A. And I'm going to use those that have 30 first. And then I have assigned 4. Let me use the ones that have 35. I have 8. So I have no other option to use 2 from the 45. And then the other 2 will be unused. Okay, so for A, I want to make sure that even though it's the second in the rank, I want to make sure that I use the spaces with the shortest distances. So that instead of using these 2, and if I use 45 instead of 30, that is incorrect. I want to use A shortest distances first, and then if I have to leave any space unused, that space that is unused will be the one that has the highest travel or weighted distances, which in this case is this corner. And that's the solution. Okay, so in summary, we have a formulation to solve this problem without having to go into this method. Like if you go and input all the parameters for this problem, if you input these parameters here and you solve using the simplex, or you use using AMPL or Excel, you will get the same solution. But if we want to avoid using the simplex method or ample, we have this heuristic that is defined here that can be used to solve the problem by hand or using an Excel spreadsheet easily. It will get the same solution. That's what we did, and this is the solution for the problem. Any questions? So the solution is basically the assignment, the final assignment for the products in the warehouse. Okay. So if you still not 100% sure of what we did, I encourage you to look at this example in the book. If you go example 1021 in your textbook, this is pages 575 pages up to pages 577. So it's a problem similar to this one that we just discussed. I think it has more doors, but again, same idea. And the solution is given in terms of figures 10.29 and 10.29C, B and C. And in the assignment, you will have practice problems that you have to solve using this method, your new assignment. Okay, so to complete this lecture on warehouses, I wanted to go back to storage systems, discuss some of the systems that are used for managing warehouses from the point of view of material handling. So some of the things that I'm going to show, the pictures and the description that I'm going to show, some of them we cover in the lecture for material handling. But again, this one is more focusing on warehouses. So rack storage systems, this is one of the primary methods of material storage. And basically the idea is to use vertical space in the warehouse. And it's very cost efficient. Okay, so you set up this, you have space, not only in horizontal space, but also vertical space to storage your product. Obviously, you need to have some type of truck to help you load and unload those products, but it's very high cost efficient. We have different rack types, walk-through, pushback, very narrow aisle, driving racks, gravity flow racks. Mobile racks, double deep racks, rollover shelf, real racks, cantilever racks. So again, whole variety of racks depending on what you want to store in the facility or the type of products that you have. So the walk-through racks, very efficient in the sense of using most of the space. Like you can leave just this type of tunnel for movement of the material handling equipment, but you are also covering or using the space at the top of the hallway. This provides easy accessibility to adjacent aisles. Picking time is greatly reduced, allow more lighting into aisles, and has higher utilization of the vertical space. The pushback racks, again, the idea is that you put the product into the racks from the back, and as you pick some of the stuff from the front of the rack, the rest of the product will move forward. So these are the pushback. So the features, pallet loads are literally pushed back into the rack. When a pallet is retrieved, the deeper pallet load automatically advances to the aisle. High density and high accessibility is used to store a large number of pallets for a long time and then remove and ship them as seasonal products. And these are typically used mostly in combination with driving racks. The very narrow aisle racks, these are typically to store products that are small in size. Permit aisle width less than 5 feet. If you're claustrophobic, this will not be a good system to use. but you are going to be working in very limited spaces, provide significant floor space reduction, use at height of 40 feet to 50 feet. Pallets are accessed with turret or side loader lift trucks. Sometimes racks are designed with top and bottom monorails. The driving racks, these are pretty common in these big stores. These are used for bulky and lightweight parts. Parts are mainly in cartons. Forklift is the material handling device used, and parts are typically stacked one over the other in large numbers. The gravity roll and flow racks, see those have these rolls inside the racks. These are used for parts in cartons. Parts are supported on rollers in the rack system. Material transfer is done with easy. They're easy to move parts along the same row as less effort is required due to the presence of the rollers. So easy to slide, move forward, a little bit more expensive than the regular ones. Mobile racks, these are very good in terms of saving space. So if you, but again, requires more time for you to unload the material. And if you're going to be storing for a longer period of time, this will be an ideal system. You can store, you can move this, and then whenever the product's needed, you go move the racks back and forward until you get the product. But if this is used for, this is not recommended for product that needs to move faster. So high density storage systems, 100% utilization of pallet positions. The storage carriers are driven by electric motors. This is used mainly in cold or ultra cold warehouse where aisle space is at a premium. And used when speed of product movement is not a major concern. Again, if you have to put something and you're sure that you're not going to be using it frequently, this is the type of system that you want to use. Ultra cold warehouses, those are expensive. Typically, they're expensive, and because they're expensive, they are not very common, right? You have to have a good justification, unless you're in a supermarket or supermarket business or medical products system, then those are going to be justified. Typically, what you will see, for example, in companies like food banks, they will have this type of storage, and if they're not using it because they don't know, for them the demand is very uncertain, or the supply is very uncertain because it's based on donations. So they will lease the space on their ultra cold warehouses to other companies if they have the space, and companies will pay for that space. Double deep racks, same idea. You want to use as much space as possible. So it's like placing two rows of racks together. Uses a deep reach lift truck for storage and retrieval, and increases floor space usage to about 60 to 65%. Used for high throughput operations, low initial cost, high productivity, and less equipment damage. If you have like products that require to be, very sensitive product, rollout shelf racks could be an option. You want to keep the product safe, at the same time, have them accessible. These are specialized storage, mainly for dedicated and costly parts, and use it for dies, measuring tools, and so on. Real racks, again, this based on the type of company that you are working on. So if you are dealing with, let's say, communications, power industry, you will see these type of storage devices. um, power production, and so on. So yes. If the company have to move those roles, um, because the way they're designed typically is not to move the rolls, but just to grab the material when needed. But if you have to move this frequently, then your objective is different, right? You're not looking at grabbing the amount of material that you need. You need the whole thing. So if that's the case, this will not be recommended. You will have another type of storage, like the racks, in which you just store the roll and you pull the roll when needed. Yes, yes. Those type in which you can stack them like they were a pallet, for example. Yeah, good question. Yeah, these ones are more designed on the sense of pulling the material, cutting a specific amount, and then using that. Fishers, this is a special type of storage, mainly for cables and wires in reels. Cantilever racks, these are typical in these stores where wood is sold, home improvements, or any type of stores that sells wood or anything for construction. But even if you go to Home Depot, you can see this type of cantilever racks. So the idea is that you have the flexibility depending on the size of the material and also the type of material. If it's heavy, if it's not that heavy, you can allocate based on what you need to be stored, what needs to be stored. But again, for long materials, construction type of materials, this is recommended. Use to store long pipes and wood. Parts are stored using the forklifts, highly economical, and can be used till heights of 22 feet. Carousel storage, these are more expensive. Like if you're running a warehouse that you require to put orders from different type of products together. Like if you have, for example, I always go back to Amazon, you can buy products that are different. You have to put an order with different products that are not necessarily stored in the same location. This allows you to have high peak rates. You can put together an order really quick. They're motorized, computer control, and independent rotating aisles and shelving. Parts are carried to the picker rather than the picker going to the parts like in the case of racks. So mostly set up in pots of 2 or 3, and pick rates vary from 80 to 100 picks per hour. Disadvantages, adding more people cannot significantly increase the peak rate, right? Because since now you're waiting for the parts to come to you, doesn't matter, you will have to wait until those parts get to you. So only one picker can operate at a given time. Thus reduces the ability of the warehouse to respond to surges in demand. So this is a picture what we are referring to. So unless you have multiple, I mean, for example, Amazon have found a different way of dealing with this. They have the carts that move AGV carts that will move the racks to you, but they are independent. They are not fixed into a rack. So if you need to bring one of those columns to the picker, it will bring a column, you pick, and then that column is moved. It will bring another column to you. And you can have multiple people requesting parts because, again, the material is not confined to a specific rail, is independent. So the cars will determine what will be the best route, where to go first, and then it can be moved anywhere in the warehouse. So pretty amazing. Try to book a visit to the warehouse as part of the class, but they still have some issues with the COVID restrictions, and they have very limited outside of hours tours. But if you have the opportunity to go visit the Amazon warehouse here in San Marcos, it will be a good experience. You can see very high technology being used for picking, which is what we are trying to achieve with this type of material handling. It is a series of rotating bins of adjustable shelves driven on the top or bottom by a motor. Rotation takes place on an axis perpendicular to the floor. Horizontal length vary from 15 feet to 100 feet. Height varies from 6 feet to 25 feet, and prices start from 5,000 and increases with the number of bins and weight capacity. So very expensive. Automatic storage and retrieval systems improve space utilization. 75% of rack space can be recovered. High saving in pickers' time allows quick access to goods via a system of shelves operating on a shuttle mechanism. Bring the exact pick store location to the operator, increases retrieval productivity by more than 2.5 times. Access area of the system is ergonomically designed to present stored items at an ideal height for picking and high employee safety and improved throughput. So these are another type of retrieval system for order picking, very automated, and it will bring the product, again, in terms of ergonomic design, it will bring the product to the height of the picker. So that's the last slide in terms of storage systems. Any questions for today's lecture? Okay, so if there's no questions, then that's all I have for today. We'll meet again on Wednesday. On Wednesday, we're going to transition to the facility location problem. So now we're going to get out of the facility, and we're going to look at if you need to place a facility in, let's say, the next warehouse for a company or the next store for a company. How do you make those decisions? Where do you place that from a geographical perspective based on the demand and the supply? So that will be covered next. Any questions? No? So I'll see you on Wednesday.